Consider the quotient group Q over Z of the additive group of rational number. The order of the element 2 by 3 plus Z in Q over Z is. To find the order of element 2 by 3 plus Z in Q over Z. In general, we can find the order of an element P by Q plus Z in Q over Z. This is additive group of rational number. So order of this element will be least positive integer such that P by Q plus Z and multiply n, means n into P by Q Z, n into P over Q plus Z belongs to Z or is an integer. Second thing we have to recall Z over nz. This is also group, and normally we know quotient group of cyclic quotient group of cyclic group is cyclic. This point is not used here, but we have recalled because we are talking about quotient group. So whenever you are trying to solve some particular problems, then always try to keep in mind, recall one or two theorem or based problems to solve this one. So order of 2 by 3 plus Z will be, we need to find. So put n equal to 2. So what we have, 2 by 3 into 2 plus Z equal to 4 upon 3 plus Z, which not belongs to in Z. So 2 is not order. Now put n equal to 3 and find n equal to 3. So 3 into 2 by 3 plus Z is equal to 6 upon 3 plus Z is equal to 2 plus Z equal to Z. Means this is an integer. And this is least. We can find integer whenever we put n equal to 6. But 6 is not least, 3 is least. So order of 2 by 3 plus Z is 3. So according to this problem, option B is correct. Let P be a prime number. Let G be a group of all 2 by 2 matrices over ZP with a determinant 1 under matrix multiplication. Then the order of this group G is. So if you remember what is SL and R, we define as all those n by n square matrices. Size of these is n by n. So you can write like this, and its determinant is equal to 1. Then we say this is special linear group of order n. So whenever is asked about to find order of SLN over FQ, this is field. Here this is real field. Then order of SLN FQ is equal to Q raised to the power n minus 1, Q raised to the power n minus Q, so on up to Q raised to the power n minus Q raised to the power n minus 1 divided by Q minus 1. This is the general formula of the order of SLN FQ. Here SLN 2 and field is ZP. So order of this one, because we are finding order of SL2, means value of n is 2 here. So and P is prime, so P raised to the power 2 minus 1 and so on up to p raised to the power 2 minus p divided by p minus 1. Now simplify this expression. We have p square minus 1 means a square minus b square formula. So p square p plus 1 product with p minus 1. This is p plus 1 product with p minus 1. Take p as a common in second bracket, then p minus 1 divided by p minus 1. So this one is cancelled out by this one. So we have p minus 1, p and p plus 1. Now check which one option is giving this one. So option A is correct here. So if you remember this formula, then it is very easy problem. Sometimes problem can be asked for GLN R. This type of problem can be asked in GLN FQ. Suppose field is this. So formula of this one is Qn minus 1, Qn minus Q, and so on up to Q raised to the power n minus Q raised to the power n minus 1. Here there is nothing in denominator. So you can write in compact form, means using product symbol. K is running from 0 to n minus 1, and this is Q raised to the power n minus Q raised to the power k. Here power is fixed and running power is k. So you can write in this way. So order of this GLN FQ is this. Let G be a group of order 17. The total number of non-isomorphic subgroup of G is, means we need to check how many non-isomorphic subgroup of G have. First need to check how many subgroup, then isomorphic or not isomorphic. By Lagrange theorem, we know that order of subgroup divides order of group, or by this consequence we know that order of element is divide order of group. If order of group is 17, then its subgroup will be divisor of 17. So divisor of 17 are 1 and 17, because 17 is a prime. So prime are, they have only two divisors, or in other terms you can say they have no other factor other than 1 and 17. So only two subgroup G has. This is itself, group itself, and this is order of subgroup is 1. This is nothing but trivial subgroup, and order of this is 1. Order of this group is 1 and not equal to 17. If we are going to check isomorphic, then E is not isomorphic to G. This group is not isomorphic to G because order of this one is not equal to order of G, because two isomorphic group have same order. So this one is not isomorphic to this, and this one is not isomorphic for this. So we have two non-isomorphic subgroup. Here this is asked, so option B is right. Let G be a non-abelian group if alpha belongs to G, means member of G, having the order 4, and beta is another element of G having the order 3. Then the order of the product of these two elements, alpha beta in G, is 6, is 12, is of the form 12k where k is greater than equal to 2, and last one option is need not be finite. J is non-abelian group. J is non-abelian group. When non-abelian is given, so in a starting point in our mind think about GLNR. This is very common non-abelian group. Also you can consider Q4 and Q4. These are also non-abelian. So you can consider Sn also. This is a symmetric group of n symbol. This is also non-abelian. So these few are examples as our mind think about non-abelian group. So this is very large, so you can restrict this symmetric group over 4 symbols. So S4 is a non-abelian group, and alpha is an element of S4. Suppose alpha, so 1 2 3 4, this is alpha, and we know that order of alpha is 4. How? Write alpha as in disjoint cycle, and the element order of this element will be the LCM of length of disjoint cycle. So this is written in disjoint cycle. So order of alpha is 4, and consider beta is 1 2 3, and its order is 3. As a given hypothesis is satisfied, and we have to find the order of alpha beta, and we have to predict order of alpha beta. So we have to find their product. So their product will be, as image of 1 is going to 2 and image of 2 is going to 3. So 1 is going to 3, and 3 is going to 1, and 1 is going to 2, and image of 2 is going to 3, and 3 is going to 4. So 1 2 3 4, all elements are used, and the order of alpha beta is 4 because of this is disjoint cycle. So as order of alpha beta is 4, so you can see is 6 option, this discard is 12, this is also discard, and 12k is of the form 12k where k is greater than is equal to 2, so this is also discard. So correct option will be option D. When order is finite means we have to find or seek some positive natural number for which alpha beta raised to the power n is identity. This is the meaning of this one. As order of alpha is given 4, so alpha raised to the power 4 is identity, and beta raised to the power 3 is identity. This is the given condition as given. So first you have to memorize some concept or some example uh, should be in your hand, so you can apply and use to discard options. So correct options for this question is option. If 5 raised to the power 2015 or 2015 is congruent to n mod 11, when n is coming from 0 up to 10, then n is equal to, so you can consider value of n should be from this set. Now we have to find the value of n. If you know the theorem, Fermat theorem, Fermat theorem, then this problem is very easy. That says a raised to the power p is congruent to a mod n, and the condition is that GCD of p and n should be 1. So 2015 can be written as 5 into 403. It's okay. So 2015 can be written as this. So we have to choose p either 3 5 because of mod 11 is given, so value of n is 11. So n for what values which make GCD 1, so value of p may be 3 5 7 9, but we have to choose only 5 because of 3 7 9, 3 7 and 9. which are not factor of 2015. So 2015 cannot be written as the product of this one. So we have only one choice for P. So consider P as 5 and N is 11. So we have to find, as the value of A is 5 given. So consider value of A is 5. So 5 raised to the power 5, which is 125 into 25, and we need to multiply it. That will be 3125, and need to divide by 11, mod 11. So what is the remainder? 11 2 is 22, 10. So we need to divide 3125 by 11. So 11 2 is 22. So what we have? 92. 11 8 is 88. So 45. So remainder is 1. So it will be 1 mod 11. It means that 5 raised to the power 5, which is congruent to 1 mod 11, and 5 raised to the power 5, and this raised to the power, what we have, 403, will be 1 raised to the power 403 mod 11, and 1 raised to the power of 403 will be 1. So it will be 1 mod 11. It means this implies that 5 raised to the power 2015 is congruent to 1 mod 11. So value of n is 1. So value of n is equal to 1, and we use the Fermat theorem to find the